Thank you, Christy.
You're welcome. Just a moment. Okay, we're ready.
Okay. Let's start. Welcome everyone to Tartaglia seminar. Today, it's a pleasure to introduce Simon Baker from the University of Birmingham. Let me say a few words about our guest. Simon studied his PhD at the University of Manchester under the supervision of Richard Sharp and Nikita Sidorov. After that, he held postdoctoral positions at the University of Utrecht, the University of Manchester, the University of Reading, and the University of Warwick. His main research interests are in the areas of ergodic theory, number theory, and fractal geometry. Today, Simon is going to talk about equidistribution results of self-similar measures.
Well, thank you very much for that that kind introduction. Yes, so maybe before I begin, if there are any points during the talk you want to ask a question or raise an issue, please feel free to interrupt me. Or if perhaps I'm speaking too quickly, also feel free to interrupt me. So so let's begin. So what is our motivating problem? So the problem I'm interested in is, suppose that we have some property which holds for Lebesgue almost every real number. And then suppose I have another measure mu, and suppose this measure is somehow defined independently from this property I was interested in. Then it's perhaps very natural and reasonable to expect that this property will hold for mu almost every x. So somehow if this property is seen as a generic property within the real line, and mu is defined in such a way that it doesn't really seek this property, then perhaps it's reasonable to expect this property to hold for a mu typical x. Often the properties we'll be interested in this talk will often be of dynamical or number theoretic nature. So let me just say one thing more. So I mean, the important detail in this problem is kind of what exactly do we mean by independently from this property? We'll see more examples from this, but this will be kind of a recurring theme in this talk. It will be somehow a measure which is independent from a property which holds Lebesgue almost everywhere. So here's a very simple result, but which I've said is a theorem, but I mean it's really just a one-line consequence of Fabini's theorem. And this theorem says that if you have a Borel set E, so imagine E is E corresponds to some property of the real numbers, and then if you take an arbitrary Borel probability measure mu, and if you translate it by a random parameter t, then for almost every t, this new measure mu t of E, so this translated copy of E, is going to this translated copy of mu is going to give full measure to the set E. So this is quite nice. So for instance, if you were interested in well, we're going to see normal numbers in a minute, but I'll mention them here. We'll define them properly in a moment. For instance, if you take the middle third Cantor set, no point in the middle third Cantor set is normal in base 3, but if you give it a random little push, then this theorem tells you that you're going to have points within it. Well, in fact, a generic point within it is going to be normal in base 3. Okay. And yes, and kind of relating this to the motivating problem from the previous slide, the idea of randomness here comes from this translation parameter, which is somehow what's giving us our independence. So the parameter t here is what is giving us our independence. Okay, so so throughout this talk, the thing we're going to be interested in is well, the property which is going to hold Lebesgue almost everywhere is going to be often in terms of a certain sequence being uniformly distributed. And the measures I'm going to be interested in are certain fractal measures. So just a definition I imagine some of us are, well, most of us are familiar with, is that if we're given a sequence xn of real numbers, then the sequence is said to be uniformly distributed modulo 1 if for every if for any subinterval of 0, 1, the asymptotic frequency which the sequence spends within this interval converges to the length of this interval. So we count the number of times xn is in the interval uv up to a point n, we divide by n, and this converges to the length of the interval. Okay, this is what it means to be uniformly distributed modulo 1. And I mentioned normal numbers on a few slides ago. Here is something a bit more detailed. So this is Borel's normal number theorem, which tells us that if you take any integer b greater than or equal to 2, then for Lebesgue almost every x, the sequence bnx is uniformly distributed modulo 1. You can see this as a consequence of the Birkhoff-Ergodic theorem and the ergodicity of the map x goes to bx mod 1. And yes, and we're going to discuss some fractal analogues of Borel's normal number theorem, well, rather analogues for fractal measures. But before I do that, I need to somehow define these fractal measures and introduce a bit of terminology. So throughout this talk, I'm going to be talking about iterated function systems. What is an iterated function system? Well, this is a finite set of contracting similarities on the real line. So this is just a finite set of maps for which you input an x and you output rx plus t, where r is some number with absolute value between 0 and 1. So it just contracts in a nice uniform way. And kind of an important result from fractal geometry states that for any iterated function system, there exists a unique non-empty compact set x, which satisfies this equation here, that x is equal to this union of its scaled down copies of itself. And x is called the self-similar set of the iterated function system. Okay, so here is a nice example. So if we would take our iterated function system to be the two maps, one map which sends x to x over 3, and the second map sends x to x plus 2 over 3, then the self-similar set for this IFS is the middle third Cantor set, which is just all those numbers whose base 3 representation only contains the numbers 0 and 2. When I'm later on in this this talk, if I'm talking about self-similar sets in a very general way and perhaps a bit lost, you could always just, every time you hear me say self-similar set, you can just think of me saying, in fact, I'm just saying the middle third Cantor set, because that's one of our main motivating examples. And for the purposes of this talk, it's fine just to think of the middle third Cantor set. So here are in this slide, we're going to define the fractal measures, which are the interesting measures we're going to be studying. So to define these measures, I need two things. I need an iterated function system, and I need a probability vector P. And with these two ingredients, it's a theorem that there exists a unique Borel probability measure mu P, which is supported on the self-similar set of the iterated function system, such that this equation holds. And this means that mu P is equal to this convex combination of its push forwards. So the push forwards are given by the elements of the iterated function system, and the weightings in this convex combination are determined by the probability vector P. And we call this measure the self-similar measure corresponding to phi and P. And this definition is, well, it's a very short and easy definition to state, but it's perhaps not, well, perhaps there are nice examples to bear in mind. So if I go back to the middle third Cantor set, a really good example to have in your mind going forwards is, well, we can see that the middle third Cantor set, every element can be coded by a sequence of 0s and 2s. So you can think about the full shift on two symbols, and any element of this full shift corresponds to an element of the Cantor set. And in particular, any measure on the full shift on two symbols, you can push down into the middle third Cantor set. And the half-half Bernoulli measure, in fact, any Bernoulli measure on the full shift, when you push it down, you get the corresponding self-similar measure. So, and in fact, self-similar measures can be defined in terms of push forwards on the full shift for where the shift has the number of the same number of digits as there are elements in your iterated function system. But yes, but going forwards, I mean, we can just think about, again, if you're not so happy with self-similar measures, we can just think about the measure on C you get where you pick 0s and 2s with equal probability. And that corresponds to a self-similar measure we'll be interested in. Well, so here we are with the middle third Cantor set again. And here is something I mentioned earlier, but let's see it again. So because, well, every x in the middle third Cantor set is not going to be uniformly distributed. Well, its sequence 3nx is not going to be uniformly distributed modulo 1. And that's because C is invariant under the map x goes to 3x mod 1. So you're always going to say in this fractal set, and there's going to be parts of the unit interval that you can't visit under the orbit of, your orbit can't visit under the action of x goes to 3x mod 1. And this is somehow, well, this is basically because C is somehow built using the dynamics of x goes to 3x mod 1. So just a simple consequence of this is that for any self-similar measure mu p, it's of course the case that 3nx is not going to be uniformly distributed modulo 1 for mu p almost every x. I mean, this is a trivial fact because, well, no point in it satisfies this property. So in particular, mu p almost every point is not going to satisfy this property, but we'll just relate it in terms of measures here for the purposes of this talk. So yeah, so as I say, the reason that there are no points which are uniformly distributed within this set is somehow the set C is built using the map x goes to 3x mod 1. So with this in mind, we can kind of pose this following very general conjecture, which I say is a meta conjecture because it's not exactly very formal. So you suppose that mu p is a self-similar measure that is independent, whatever independent means, from the dynamical system x goes to bx mod 1. Then it's reasonable to expect that for mu p almost every x, the sequence bnx is going to be uniformly distributed modulo 1. So somehow, I mean, the important detail here is this word independent here, right? I mean, what do I mean by independent? And this is being deliberately vague, but somehow it's somehow reflecting the ideas behind studying the whether there are normal numbers in these fractal sets. Okay, so this meta conjecture has been verified in certain cases. So the first case it was verified was in 1959 in a paper of Castle's, and he considered the middle third Cantor set, and he considered the half-half self-similar measure. So this is the measure which you pick digit 0 or 2 with probability at half, the image of this Bernoulli measure on the shift on 2 symbols. And he showed that if B is not a power of 3, then the sequence bnx is uniformly distributed modulo 1 for mu almost every x, where mu is this half-half self-similar measure. So somehow when I speak about the independence here, you could somehow think that, okay, because B is not a power of 3, and the fact the middle third Cantor set is very much built using 3 and powers of 3, that this is enough independence here. Somehow the number theoretic independence between B and the number 3 is going to somehow filter down through into the Cantor set, and this is going to be enough to guarantee that almost every point of the sequence bnx is uniformly distributed modulo 1. So a nice generalization of this theorem, which was proved much more recently, is due to Mike Hockman and Pablo Schmerkin, and they considered more general iterated function systems. So here notice that we have iterated functions with potentially different contraction ratios here. We could have different contraction ratios, and we also assume the iterated function system satisfies some additional separation assumptions, but they're technical and not really relevant to this talk. Then if you have take an integer of b greater than or equal to 2, and if you can find a contraction ratio such that the log of the absolute value divided by log b is an irrational number, if you can find a contraction ratio which satisfies this, then for every self-similar measure mu p almost every x is such that bnx is uniformly distributed modulo 1. So somehow
Simon,
oh,
sorry.
Yeah.
just can you explain a bit what you mean by separation assumption?
So, well, I'm being kind of very deliberately vague here. I mean, there is a technical thing you could put down here, but okay, so one thing you could do is if you think about okay, so one particular case where this would be satisfied is if you remember this equation I wrote on the bottom here, that there exists a unique non-empty compact set X, which such that X is equal to this union of its images. If this union was disjoint, then that would be enough for this theorem. Okay. Okay, I assume that's
yeah, fantastic. That's okay. It. Yeah, thanks.
But somehow, if we try and rephrase this in terms of our motivating question, in terms of independence, well, somehow here we have that this fact here that the logarithm of a contraction ratio divided by log b is irrational. This is somehow showing that there's somehow some measure of independence between the parameter b and the contraction ratio Ri. And this, again, this independence filters down into the self-similar measures on this iterated function system, and it guarantees that for these self-similar measures, a typical point is going to be is going to be normal in base b, or that bnx is uniformly distributed modulo 1. And another theorem which I quite like, which is due to Desjardins, Ganguly, and Weiss, says that if you look at iterated function systems for which the contraction ratios are all the same, and in fact they're going to be the reciprocal of the base that we're interested in, so we have x goes to x over b plus some translation. If you can find two translations such that the difference between them is irrational, then again, for every self-similar measure mu p almost every x is going to be such that bnx is uniformly distributed modulo 1. So somehow, again, this independence here comes from the fact that you have two translation parameters whose difference is irrational. Okay, and yes, it's also worth mentioning some other works which are due to Kaufman, Quefelec and Romare, and Jordan and Solston. And what they did is they considered certain fractal measures and studied their Fourier transform. And you can show that if the Fourier transform of a fractal measure decays to 0 sufficiently quickly, then mu p almost every x is going to be, well, for mu p almost every x, the sequence bnx is going to be uniformly distributed modulo 1. So somehow you can think of the works of these last few authors, they study the Fourier transform, so somehow they prove something stronger. They prove some decay properties of the Fourier transform, and from these properties you can then deduce that you have certain uniform distribution results for mu typical points. So yes, so the motivation behind this talk comes from these previous theorems, which are somehow fractal analogues of Borel's normal number theorem, and this theorem here, which is due to Koxma. And this is somehow, if you were to read a book on uniform distribution, the first theorem you'd probably read would be Borel's normal number theorem, and the second theorem you would read is this one due to Koxma. And this tells you that for Lebesgue, almost every x, the sequence x to the n is uniformly distributed modulo 1. So I'm interested in somehow if I can prove a fractal analog of this theorem, in particular for self-similar measures. So here is a conjecture which perhaps motivates what I'm going to be talking about. And it's that if you have, suppose you have some non-atomic self-similar measure mu with support contained in, well, the interval from 1 to infinity. Of course, we need this assumption. Then it is the case that for mu p almost every x, the sequence x to the n is uniformly distributed modulo 1. Okay, so the reason why I could expect this to be true is because, well, our iterated function system consists of affine maps. They just send x to some scale copy of x plus a translation. So these are affine maps. And the property we're interested in, well, this is in terms of higher powers of x. So in particular, they're certainly not affine. So it's reasonable to expect that because somehow our measures are defined using, somehow you could think of them as affine objects, and the property we're interested in is not an affine object, sorry, is not an affine property, then it's reasonable to expect that these so affine objects, these affine measures, are going to behave like the Lebesgue measure in that they're going to give full mass to those points for which x to the n is uniformly distributed modulo 1. Another perhaps more general way of thinking about this is somehow you could think of the iterated function system, well, the self-similar measures are somehow dynamically defined measures. And this property that x to the n is uniformly distributed, well, as far as I know, and I think it is the case, but there's no dynamical system you can study which gives you any kind of meaningful information about the distribution of x to the n modulo 1. In particular, there's no dynamical proof of this theorem of Coxma. Okay, we have to use different methods, and it's more number theoretic in flavor. So again, somehow you could think of this property of the powers being uniformly distributed modulo 1 as being a non-dynamical property. And then you could ask yourself, okay, is it true that a dynamical measure, like a self-similar measure, is going to give full mass to the set of points which satisfy this property? So it's, yeah, if I'm feeling a bit bolder, I think of it as some kind of independence between a non-dynamical property and a dynamical measure. Okay. Maybe just, are there any questions at all at this point before I move on? Oh, there's something in the chat.
It's okay.
There's no questions.
No, but in that sense, yeah.
Oh, sorry, I just saw I saw the chat light up, but okay, if it's fine, I'll carry on. So okay, so now we're going to start kind of formalizing my results. So for the rest of this talk, we're going to be talking about echo-contractive iterated function systems, and these are just when the contraction ratio is always the same number. So this is a bit like the middle third Cantor set again, where we always contracted by 1/3. Now we're always going to contract by some parameter r. This is not such a restrictive condition. What is a slightly unusual condition is this convex strong separation condition, which is that I'm going to assume that my iterated function system is such that if you consider the convex hull of the self-similar set and you consider its images under the elements of the iterated function system, I'm going to assume they're going to be disjoint if the maps aren't equal. So you could think of this property as, well, both these properties are satisfied by the middle third Cantor set because we have contraction ratio 1/3, and the convex hull of the middle third Cantor set is the interval 0, 1, and you contract one image is 0 to 1/3, and the other image is 2/3 to 1, so they're definitely disjoint, as we see here. So the theorem I'm going to formulate is going to be in terms of iterated function systems which satisfy these two properties. And, well, perhaps unsurprisingly, I'm going to prove a uniform distribution result for x to the n, well, the sequence x to the n mod 1. But in fact, the theorem holds more generally for more general sequences of functions, but they need to satisfy several properties. So I'm going to state these properties here. This will be a bit technical, so if if it's confusing, you can just ignore it and think that Fn is always going to be the map which sends x to the n. So I need each Fn to be 3 times differentiable on the convex hull of x. And I need, well, 2 constants C1 and C2, such that the first derivative of Fn minus the first derivative of Fm in absolute value is going to be at most some kind of polynomial growth term n to some power multiplied by x to the power of n minus 1. So this is obviously true when Fn of x equals x to the n. Or, well, it's maybe not obviously true, but it's a simple exercise just to check this is true. I need a lower bound on the difference of the derivatives, the second derivatives of Fn and Fm. And I also have this property here that if you fix 2 parameters m and n such that m is less than n, and you consider their third derivatives, the difference of their third derivatives, we need them to either always be always positive, or rather positive for all x or negative for all x. I realized when I gave this talk earlier, I realized there's some slight ambiguity here. And you don't need it to be, well, for any m and n, you either need them to be, the sign here can depend upon m and n. Okay, you don't need it to be the case that for any m and n, it's either always positive, or for any m and n, it's always negative. It's either the case that for m and n, you can see, okay, for a particular m and n, when I look at the this quantity, it's either going to be positive for every x, or it's going to be negative for every x. But for different values of m and n, you can see the greater than or equal to be less than or equal to. But anyway, I mean, we're only interested in x to the n, for which these are always we're always going to be in the positive case. But some other interesting sequence of functions which the results can apply. So in particular, functions which satisfy these properties. So we have the familiar x goes to x to the n, or I could take the sum of each of the powers up to n, or more generally, if I take a sequence of polynomials with, well, more generally, if I take a sequence of polynomials, I can, well, rather, if I take another polynomial and I multiply this by x to the n, there are lots of ways I can build sequences of functions fn for which I'm going to be able to prove some results. So here's the main theorem, and this again is a bit complicated. We'll see a simplified version of it in 2 slides. And it tells us that if we have an equicontractive iterated function system which satisfies this convex strong separation condition, and also we need the self-similar set to be contained in this interval from 1 to infinity. And if I let fn be a sequence of functions satisfying these properties I mentioned before, then, well, we'll mention some property of the self-similar measure in a moment, but then for mu p almost every x, the sequence fnx is uniformly distributed modulo 1. Okay, so what property do I need for myself that I need my self-similar measure to satisfy? I need this quantity on the right, which is the entropy of the probability vector divided by minus log r, which you can think of as the Lyapunov exponent. This needs to exceed 1/2. And this is very much a technical condition. Okay, this is somehow a consequence of our proof. But a nice way of thinking about this is this quantity on the right is in fact, well, this is the dimension of the measure. I haven't defined what the dimension of the measure is, but somehow you could think of this quantity on the right as being some notion of size of the self-similar measure. So somehow this theorem is true if the self-similar measure has large enough size. It's another way of thinking about it. Here's a corollary, but we'll ignore that one. Here's a nice corollary, which is really the theorem I set out to prove initially, which is that if you have C as the middle third Cantor set, then for any parameter t greater than or equal to 1, if you translate the middle third Cantor set to C plus t, so in particular, it's now going to be in the interval 1 to infinity, then with respect to the Cantor-Lebesgue measure on C plus t, almost every x, its powers are going to be uniformly distributed modulo 1. And yeah, here we're just using the fact that this Cantor-Lebesgue measure is the half-half self-similar measure. It's simple to check that the self-similar measure is going to satisfy this inequality here, because we get log 2 divided by log 3 in this case, and then yeah, it's a simple check that this is going to be greater than 1/2. Okay, so let me say a bit about the proof now. So yes, so this is kind of very different from some other works on the sequence BNX mod 1. So in particular, we don't use any properties of the Fourier transform with the self-similar measure, which is what Cassel's did. And in particular, well, for certain self-similar, well, we're trying to study all self-similar measures, and our theorem is in fact for a broad class of self-similar measures, including those whose Fourier transform does not decay to 0. So in particular, we can't really use, we can't really depend upon the Fourier transform to prove our results. Otherwise, perhaps we could reinterpret our problem using some harmonic analysis and then use some good decay bounds to say something, but we can't do that here. And we also can't use techniques from ergodic theory, and that's simply because of this fact I mentioned before, that the sequence x to the n mod 1 is not really dynamically generated. So what our proof does is it really exploits the fact that our sequence of functions fn are not affine maps. So somehow we need to study kind of uniform distribution kind of through the right lens so that we can exploit the fact that these maps are not affine. So, so yes, so the way we're going to prove our uniform distribution result is using this very useful proposition, which is kind of a combination of, well, this well-known Weil's criterion for uniform distribution, which somehow rephrases uniform distribution in terms of sums of the sort of the average behavior of each of the 2 pi I L xn, where xn is your sequence. And somehow this average converged to 0, then xn is uniformly distributed. Or rather, you need this property for all L, so each of the 2 pi I L. But what is less well known is this result of Davenport, Erdős, and Levesque. And it tells you that if you have a, well, we've kind of rephrased this a bit for our purposes, but if you have some Borel probability measure and Fn is a sequence of continuous real valued functions, then if at any L, this quantity converges, then for mu almost every x, the sequence Fnx is uniformly distributed modulo 1. Okay, so just a little extra comment on this somehow. Well, it's a bit, let me just, what's the best way of phrasing this? Okay, so somehow you might think, okay, how is this going to relate to uniform distribution? I mean, we see this sum on the inside, which is somehow the sum which is relevant to Weil's criterion, but how do we go from somehow this converging to some typical information? And kind of the, well, it's not a trivial argument, but the point is somehow that we're going to use the first Borel-Cancelli lemma. So in particular, we're going to have this is less than infinity. And then we're going to be able to reinterpret this using the Borel-Cancelli lemma. And if I remember correctly, Markov's inequality. And this is going to tell us about the measure of certain sets which exhibit exceptional behavior. And this is going to be a small set. And then this is going to be enough to guarantee that for a large set, this quantity on the inside is going to converge to 0. And then we can apply Weil's criterion. Anyway, that was just kind of a bit of a ramble, but maybe it was instructive for some people. Okay, so with this proposition in mind, kind of the game is now to show that this is true for any parameter L. Okay, so now we set ourselves to proving this, and the proof kind of splits into 2 parts. The first part, what we do is well, naturally we end up considering certain integrals that are defined in terms of our self-similar measure, and we're going to bound these from above in terms of the L2 norms of certain functions which are defined with respect to the Lebesgue measure. Okay, and somehow the Lebesgue measure is going to be easier to work with. And in the second part, we're going to study these new Lebesgue integrals, and we're going to do some careful analysis. In particular, we're going to use a lemma from harmonic analysis called van der Corput's lemma. And this is going to give us good upper bounds for the for these integrals which are defined with respect to the Lebesgue measure. And this is the point where we're going to use the fact that the sequence of functions Fn is non-affine. So kind of for convenience, for the rest of this talk, we're just going to think about this iterated function system, which sends x to x plus 2 divided by 3, and another map which sends x to x plus 4 over 3. And we're going to think about the half-half self-similar measure. And the reason we're going to restrict to this, well, for this case, the self-similar set is just the middle third Cantor set plus 1. Okay, so this is a very natural, example. And we're also, oh yes, we're also a bit of notation. So if I have a sequence of zeros and ones of length m, then I'm going to denote by phi subscript a the concatenation of those maps corresponding to the individual elements in the word a. So, we apply the map corresponding to the mth digit, then the m-1th digit, all the way up to the first digit. Okay, and also for convenience, I'm going to let c subscript a equal the image of c plus 1 under the map phi a. This notation is a bit messy. I was a bit unsure whether to put c plus 1 subscript a, but I thought that would get a bit messy. So this is slightly confusing because somehow c previously was the middle third Cantor set, and I'm putting this c subscript a But what I'm really thinking about is the image of C plus 1 under this sequence of maps. Hopefully this is clear. But yes, so maybe just to go back, remember we want to show that this is true for any L. So if you expand the square here, you very naturally end up considering integrals of this type. So you have fnx minus fmx for n greater than m. And here we've introduced a bit of notation that e to the 2 pi x is going to be replaced by exp of x, just makes things easier to write. And the first trick we use is we use self-similarity of the measure. So remember, the self-similarity of the measure tells us that the measure is in fact equal to this convex combination of its push forwards. And we can iterate this relation m times. So in fact, somehow you can think of the convex combination of its push forwards as being the images under the words of length 1 with appropriate weights. But we can iterate this and in fact show that the measure is going to equal the convex combination of its images of any words of any given length. So in particular, in this expression, I'm interested in words of length m, where m is some parameter which is carefully chosen, and I'm going to sweep a lot of technical details surrounding m under the rug, but m is going to be some natural number. And yes, so when I consider the push forward of word, if I iterate this defining property of self-similar measures to consider words of length m, that allows me in this integral to replace my function here with this function wmx. Okay, notice we're seeing push forwards because instead of having x in here, I have phi subscript a of x. And instead of having 1/2 here, I have 2 to the m, and this is because we're considering words of length m, and they're all going to have mass 1/2 to the m. Okay, so yes, so now instead of integrating this function, I'm integrating this function, and this is well, I'm going to comment a bit more on this later, but is this something quite interesting happening here? So the first step in the proof is I look at all those words of length m for which this quantity wmx is going to exceed 2 multiplied by 3 minus delta n. So somehow you could think of these words rm as going to be those words which for which the sequence wmx is not exhibiting any exponential decay. You can think of delta as being some very small real number. Somehow in the word, you have a word, so rm is somehow those sets of words for which you have a point for which the function wmx is not seeing some very weak exponential decay. Okay, and the first thing to comment upon is, well, if you consider the complement of these words, well, then you can have some exponential decay upper bound on this integral restricted to these words. So in particular, if I was just to, instead of considering wmx integrated over the whole of the translation of the Cantor set by 1, I just would consider those pieces of it corresponding to words of length m which aren't in the set rm. Well, for any one of those, I can bound the function wmx above by 2 multiplied by 3 minus delta n, and that's going to give me this inequality here. So in particular, this piece is having some good exponential decay already. Okay. So here is kind of a useful fact, which is that if I pick my m in a special way, if a was in rm, remember rm told you there was a specific point for which wmx exceeded 2 multiplied by 3 to the power of minus delta n. Well, if I pick my m in a smart way, it's in fact true that if a is in rm, then for every x in the in this interval here, the image of the interval 1, 2 under the map phi a, every point in this interval is going to the function wmx is going to be at least 3 to the power of minus delta n. Okay, for every x in this interval. This is just doing some clever calculation and using the mean value theorem. If you pick your m in the right way, you can guarantee this is going to be true. Okay, and using this fact, we're going to now be able to relate this integral with respect to the fractal measure in terms of an integral in terms of the Lebesgue measure, and that's kind of what's on here. And it's a bit of a mess, but maybe if I go through it slowly, it will be clear. So here we're integrating our function wmx over those. Well, we're looking at those pieces corresponding to those words in rm. So these are the bad words. And well, each one of these pieces has measure at most 1 over 2 to the m, and Wmx has absolute value 1. So in particular, this is a really trivial upper bound, right? Wmx has absolute value at most 1. This, the measure of Ca is 1 over 2 to the m, so we get this. Really nothing clever here. Then what I do is I take out this factor 1 over 2 to the m, and then I multiply by 3 to the m and 3 to the minus 2 delta n, and then similarly 3 to the minus 2 delta n divided by 3 to the m. So notice these just cancel. So I mean, this is just multiplying by 1 in a clever way. And then we focus on this summation here. And notice that I have this 3 to the minus delta n. And in particular, we know that if you have a bad word Rm, and if you have a point which is in the image of the interval 1, 2 under the map phi a, then you know Wmx is at least 3 to the minus delta n. So in particular, its square is going to be at least 3 to the minus 2 delta n. Okay, that's just using this property here. So what I do here is I use this fact together with the fact that every that the length of this interval is 3 to the m. Okay, because this is just an interval of length 1, which is contracted by 3 to the map of with contraction ratio 3 to the m. So I get a 3 to the m here. Okay, so this is an upper bound for this. And then in the last step here, all I do is I consider, well, I know these, I know phi a of 1, 2. I know these intervals are disjoint, and I know they're all contained in the interval 1, 2. So I just say, well, let's just consider the integral over the whole of 1, 2. Okay, and this is going to give me an upper bound. So you see, I've related my my integral with respect to my fractal measure to something in terms of the Lebesgue measure. And but there's a real problem with this. Let's remember, we're trying to show that these integrals are going to be decaying to 0 sufficiently quickly, because we wanted to show that this summation which arose from this Erdős, Davenport, Levesque and this Weil criterion was going to be finite. So I want to get some good upper bounds here. But what I've got at the front here is 3 to the m, essentially 3 to the m divided by 2 to the m. We kind of ignore this 3 to the minus 2 delta n here. So I have this term which is growing exponentially in m. And somehow I'm going to need to show the thing with this integral in here is going to be decaying sufficiently fast that it's somehow going to beat this 3 to the m divided by 2 to the m here. I need to I need to get these things to balance out against each other. Well, in particular, I need the Wmx to decay sufficiently quickly that it's going to beat the 3 to the m divided by 2 to the m. Another thing to comment upon, and you can kind of see here why this why I needed this lower bound of a half in the dimension of the measure. And that's because, well, 3 is the Lyapunov exponent and, well, kind of corresponds to the Lyapunov exponent. And 2, well, this is e to the entropy. And if you think, okay, if the entropy divided by the Lyapunov exponent was closer to 1, well, the corresponding parameters 3 and 2, well, they would be replaced with some number which was still greater than 1, but which would be closer to 1. So in particular, the larger the dimension of the measure is, the more this exponential term here, this 3 divided by 2, is going to get closer to 1. And this somehow kind of corresponds to your intuition, because somehow here we're kind of fairly crudely going from a fractal measure to the Lebesgue measure. And somehow you can see that how effective this approach is somehow determined by how large the measure is in terms of its dimension. If you have large dimension, this annoying exponential term, which is going to fight against you, is going to be relatively small. Okay, so yeah, it's just an aside there. So yeah, so just combining everything I've said, what I'm left with is, well, I had my piece corresponding to those nice words, which I saw exponential decay. So I have this 3 to the minus delta n, and I have this thing left over here. But it suffices just to kind of start looking at this integral on the inside here. Let's try to get some upper bounds for this integral. Sorry, this slide is just basically repeating what I said, that this error term at the front of the integral somehow arises because of the kind of the innate inefficiencies in this argument, and this is why we need these this dimension lower bound. Remember, this quantity on the right hand side is a measure of the size of the fractal measure. So yes, so to complete our proof, we need to get good upper bounds on this integral here. So just to recall that this is what Wmx is. So perhaps it's not unreasonable to think, okay, well, if I was trying to get bound for the L2 norm of Wmx, well, we're very naturally going to end up looking at integrals which are of this form. Okay, so the important thing is I have distinct words A and B, and I'm looking at, well, fn minus fn evaluated at phi a of x, and I'm subtracting from this fn plus fm evaluated at phi b of x. Okay, but importantly, A and B are distinct here. So we want to get some good information on these integrals here. So how are we going to do that? Well, we're going to do that using this van der Corput inequality, which is, say, this technique, I think, perhaps, yeah, kind of sits partially in harmonic analysis and partially in number theory. And this tells you that if you have a function phi from a closed interval to the real numbers, and you assume that phi has a uniform lower bound on its derivative, and if you also assume that its derivative is monotonic, then you can get some upper bound on this integral here in terms of the reciprocal of the derivative. And it's quite an interesting fact here that this bound somehow is independent of the parameters a and b. You can have any a and b here, and you're still going to get this 1 divided by gamma term here. And this letter has a really nice interpretation, because if you think that if you were so what is this saying? Well, we think about our function phi x. So phi x has some lower bound on its derivative. So if you think somehow the derivative is telling you how quickly you're going round the circle, going round the unit circle, and somehow if you were to go round the unit circle very, very quickly, and if you were speeding up, then somehow you're going to spend kind of on average a uniform amount of time in each part of the circle, and this is going to force this integral to be small. So it has a nice kind of physical interpretation as well, which I like. And yes, so we're going to apply this van der Corput inequality, and this is where we're going to use the fact that our functions fn are not affine. So yes, we would apply it to these integrals on the bottom here, but this is a bit technical and messy, so I'm not actually going to give those details here. But I want to mention, well, you know, this is where the affine property is used. So let's just see where it breaks down. Or rather, so we're going to use the fact that our sequence of maps fn is not affine. So let's see where this breaks down for some nice affine maps like 3nx mod 1, for which we know, well, c plus 1, no points in that set are going to be uniformly distributed under for no points in that set is the sequence 3nx mod 1 going to be uniformly distributed, because they're always going to be still in the middle third Cantor set. So how does this break down? Well, if I wanted to apply van der Corput's inequality, I would want to calculate the derivative, and the natural choice for phi here is this quantity here. But if you apply the chain rule, you can in fact show the derivative is 0, which is which is why the proof breaks down. And this is why it's very important that the sequence of functions we're considering are not necessarily affine. Okay. Oh yes, so I really wanted to emphasize one feature of this argument, which I think is very very subtle but quite nice and clever. So suppose we wanted to bound this integral, which is, you know, an integral we've seen previously. So, you know, a very kind of useless thing to do would be to say, okay, let's just take the absolute value inside of the integral, because then, well, the thing we're taking absolute value of is just going to be 1, right? So this is just going to give us an upper bound of 1, which is pretty meaningless and isn't going to help us at all. But if we think about self-similar measures, well, remember they had this useful scaling property which allowed us to show that the integral of this function is in fact going to be the integral of this function in here, okay? And it's certainly the case that, well, this function can decay in terms of, or rather the absolute value of this function can decay to 0. So with that in mind, if you then take the absolute value inside after swapping these functions, what you can get is going to be meaningful. So this is a really kind of clever, useful thing which self-similar measures allow us to do. We want to do this kind of naive trick of just bringing the absolute value inside. But this is kind of pretty meaningless if you're looking at integrals involving e. Self-similar measures allow you to replace e with this different function, for which then if you bring the absolute value inside, what you get is meaningful. And yeah, and it's very reasonable to expect that this quantity will in fact be small, because you have this different you have different information from different parts of your set, and somehow this is picking up on different parts of your set. So it's reasonable to expect that this this quantity could be small. Yeah, so maybe I'll just say one very brief thing and then stop. So if you consider more general self-similar measures, so in particular if you have non-uniform weights, so remember kind of throughout this, we've seen this 2 to the m appear throughout. And this is just because all the words of length m have weight 1 over 2 to the m. If your probability measure has different weights, then things are slightly more complicated. But what you can do is you can use some sort of large deviation estimate, which tells you that outside of an exponentially small set of measure, the typical behavior of, well, the typical measure of a cylinder of length m is basically going to look like e to the minus log of the measure theoretic entropy. So basically that means when you kind of do your analysis, instead of having a 2 to the m here, you're going to have lots of terms which look like e to the minus log of the entropy, maybe with some small error on the end, but essentially e to the minus log of the entropy to the power of n. But that was all I wanted to say. Thank you very much for listening.
Thank you, Simon. Are there any questions or comments in the audience?
Well, yes, no.
Sí. Gallo.
Yeah, just a question, comment, just to be sure I understood. Well, so if you take any, you have this full shift, which codifies your Cantor set, and if you take any shift invariant measure, this will give you a self-similar measure, is it?
No.
No?
It has to be a Bernoulli measure.
Has to be, okay, so my question is, what about other fractal measures which are not self-similar?
So,
can you say something? Because you can assume they are invariant under the shift for the coding, and then you have the same argument with the entropy as you mentioned just a few minutes ago.
I think I wouldn't be able to do this trick I mentioned here, though. But remember, it was this very important that I could freely go from this integrating this function to this function here. And for general measures on the shift, yeah, I don't think.
I see. So
yeah, no, I don't think it. Yeah, I don't think you could do this step, and this is a very critical step.
But what do you think about the result? Maybe the result holds even if you cannot.
I would. Yeah, it seems extremely likely. I mean, as I say, somehow this. You know, if we think about this in very broad terms, as I say, it's somehow a non-dynamical property, and we're looking at a dynamical measure, and somehow these things shouldn't interact, and somehow the measure, the dynamical measure, should just, you know, basically behave like Lebesgue measure in terms of this property. So certainly, I'd expect, well, except, you know, apart from stupid examples, you know, like you know, a measure which is supported on a periodic orbit or a fixed point or something. But you know, if you have something with positive entropy, I would expect, yeah, its push forward onto the Cantor set would almost surely, you know, a mu typical point, its powers would be uniformly distributed.
Okay, thank you.
Can I ask one?
Yeah, sure.
I was just thinking, because your results are always in on the real line. So what do you think about, could you think about an extension of these kind of results for, say, IFSS in R2? Satisfying the same condition, the convex separation condition?
Yes. So, well, there's nothing I've proved explicitly in this direction, but I certainly think it is the case that for certain higher dimensional sets you can prove something. I think so. Kind of an obvious example would be. Actually, would it be an obvious example? I think if you were to take something like the Sierpinski gasket, so imagine you take the unit square and you chop it into 9 squares of size 1/3 by 1/3, and you remove the middle piece, and then all the remaining middle pieces from the remaining pieces, and so on and so forth. I think you could probably prove a result for a set like this because, well, what you might end up doing is thinking about you would perhaps disintegrate your measure along the fibers, and these would kind of look like self-similar measures, and then you could prove some results in this direction there. And I think also you can maybe prove something for like bedfoot mullen carpets here like that. But just for general self-similar sets, no, I'm not sure. I think there are some. Yeah, it can be a bit more complicated because, yeah, somehow you have to yeah, somehow if you think about what's going on in the real line, and you think about the function x to the n, somehow it's obvious, okay, if you move from left to right, you know x to the n is just increasing, its powers are going up, and this is a simple, obvious fact. But now imagine if I have something like, imagine I was to look on 2 dimensions and I was to look at something like x to the n plus y to the n. Then it's not quite so simple as to say, okay, if you go to the right, you go up, and to the left, you go up, because you have all the different directions in R2. And in particular, you could pick a point and then travel in a direction such that x to the n plus y to the n is going to kind of look like what you had originally. So this means that, so this is kind of an added technical difficulty. And this is one of the reasons why it works well when you consider these, if this example I described to you, when you kind of disintegrate your measure, along certain fibers, because then essentially you're just in the one-dimensional case. And then when you travel in a particular direction, things are simple and straightforward. You're just going, you're just going up or you're just going down. You only have really one direction to think of, which simplifies things.
Okay, and I have another one. Can you go back to the convex condition, the convex separation condition?
Yeah, sure. Yeah, here we are.
Yeah, there you go. So you need always this kind of a strong separation thing. So like, how is there any kind of way to relax this condition in order to get a result like this?
Well,
just think about, like, just consider the open set condition.
Yeah. So, well, for the method of proof I give, actually, it's very important that this property is satisfied, and I'll explain to you why in a moment. But I actually think it's the case. Well, this is. Yeah, so it's very natural to say, okay, can you reduce the open set condition? I think you can actually reduce this property quite significantly, and even have examples where the open set condition is not satisfied and have some kind of very properly overlapping iterated function system for which you can prove a result like this. But this is, I certainly don't know all the details to this, and is very much work in its infancy and work in progress. But let me just explain to you why this is quite so important to me. When I am looking at this integral here, okay, so we have a point x, and then we're looking at the images of phi ax, phi x, phi bx, phi bx. And remember, the point X is in the interval 1, 2, and this is the convex hull of C+1. So this, so we know because of this convex strong separation condition that the images of 1, 2 under the maps phi A and phi B are going to be disjoint. So the point here is that that tells me that the distance between phi A of X and phi B of X is going to be at least some uniform constant. They're going to be roughly they're going to be at least 1 divided by 3 to the m apart, I guess is what I'm saying. And that's extremely useful. And you really need this to then properly apply to get some good bounds for van der Corputz inequality. Because if you imagine if phi A and phi B were very close, phi A of X and phi B of X were very close to each other, well then this quantity here is just basically going to look like 0 for a lot of X's, which means that you're going to basically just be looking at exponential of basically 0. So you're going to be looking like well, this is just going to look like 1. So you're not going to get a good upper bound on the integral. So this is why this separation tells you that you can't really have large parts of the subspace for which this quantity is going to be such that the quantity you're evaluating your exponential at is going to stay close to 0.
Okay, thanks.
I also have a question, Simon.
Sure.
So you had a conjecture for self-affine measures. So your main result or your main corollary, this is the case where the iterative function is, I mean, it was equicontractive, so the R's are constant, and this is also the case when the T's are constant, right? Your self-affine measure that sends the one generated by C plus T.
Oh wait, I think
so your corollary.
Yeah, where it's sorry. Let me just find it, and then I'll be. Oh, yeah. So here we are. Yeah.
Yeah. So this corollary, this is a special case of the conjecture, right?
Yes. Yeah.
And this is the case when the iterated function system is the simplest, right? When.
Yeah, it's equicontractive, and it has this very good separation property.
Yeah, but it's equicontractive, and the separated property comes from the. So I mean, basically, you have here. So what I mean, my main question is what's like the natural step that your technique does not cover. I mean, the simplest. What would be like the simplest example of a self-affine measure that your technique does not cover?
So a simple example would be something for which this inequality was not satisfied. So in particular, if you were to take a self-similar set of dimension strictly less than 1/2, and any self-similar measure on this, well, this is also going to have dimension less than 1/2. So yeah, so I couldn't.
So, but this here you also change the fractal, right? If you change this, the fractal generated by the system.
Yeah. So if the fractal is a smaller dimension, but sorry.
And if you want to stay on the Cantor.
Just staying on the Cantor set. Well, I mean, basically, this theorem covers every case you could reasonably expect for the Cantor set, because, you know, well, in terms of self-similar. Oh, sorry. Okay, so for self-similar measures, yeah. So this would then correspond to maybe you'd have to pick your self-similar measures to be in a non-uniform way. So maybe if I was to pick a self-similar measure. So I have a P and a P1 and a P2. If P1 was maybe 0.99 and P2 was 0.01, then then the entropy is going to be too small for my techniques to apply.
Okay.
Okay. Yeah.
So the don't. Okay, I see. Thanks.
Are there any other questions? Okay, well, Simon, thank you very much for your presentation. And we conclude today's seminar. See you next week.
That's right. Thank you. Thank you for having me.